In this lecture, we are going to see the topic that is related to the analysis of proper cantilever beam subjected to a UVL, that means uniformly varying load, which is having maximum at the fixed support and zero at the prop support. Coming to the question, determine the reaction components for the proper cantilever beam subjected to uniformly varying load as shown in figure. Draw shear force and bending moment diagrams. Coming to the figure, so this is an AB which is having a span of length L, and for this A support is a fixed support and B support is a roller support, and here the load is uniformly varying from W kilonewton per meter, which is at the fixed support, that is maximum load, and from A support to B support it is uniformly varying. That means at A you are having a maximum load of W kilonewton per meter, and at the B support you are having a 0. So it is varying like W to 0. So for this beam, you are going to analyze first and then find out the reactions. After determining the reactions, with the help of the reactions and all, you are going to draw the shear force and bending moment diagrams. So before that, first you are going to find the degree of static indeterminacy. So as we know that A support is a fixed support, here you are having three reactions. So one is horizontal reaction HA, another is vertical reaction RA, and another is moment MA. And at the B support, as it is a roller support, you are having only a vertical reaction, that is RB. So therefore, total number of reactions here are 4. We have number of static equilibrium conditions to be 3 in 2 dimension, that is sigma fx, sigma fy, and moment about xy is 0. Therefore, the total degree of static indeterminacy is 4 minus 3, that is 1. Now you have to balance your forces. So by considering sigma fx is 0, that is summation of your horizontal forces. As you can see that there is no external horizontally applied load in this beam, on this beam. Therefore, HA will be equal to 0. And similar way, sigma Fy equal to 0. That means the total load, external load coming onto the beam will be equal to the opposing reactions at A and B supports, that is RA and RB. Since you are having, it is a uniformly varying load, so the total load will be equal to area of this triangular pattern. So the area of this triangle is half into the load here is W into the span here is length. So half W into L, that is WL by 2. Therefore, the total load will be equal to WL by 2. Therefore, RA plus RB will be equal to WL by 2. So this is an equation we are getting from sigma Fy equal to 0. Coming to the next one. Here you are going to choose the redundant force or redundant reaction also you can say. So as we know that this is a given beam, proper cantilever beam, which is having a uniformly varying load. So now this proper cantilever beam is assumed to be consist of 2 parts. So first part is nothing but a simple cantilever beam. You can see here, this is a simple cantilever beam, which is carrying a uniformly varying load only. So here I am removing the roller support. So this is a basic cantilever beam with a UVL. And next is you are going to have another cantilever beam which is having a reaction RB at the B support. Instead of this prop, I am inducing a RB reaction at this B support. Therefore, by superimposing these two things, we are going to get the proper cantilever beam. Here we can say that vertical RB is treated as a redundant force. So we are going to find out the RB first, then we are going to find out the RA reaction, then finally moment you are going to find out at the A support. Coming to the next slide. So what we are going to do is, in this slide we are going to calculate the reactions. So to calculate the reactions, what I am going to take is, I am going to balance the deflection at this end point, that is B support. So as we know that we have considered this entire proper cantilever beam into 2 parts. One is simple cantilever with the UVL and another is a cantilever with the upward reaction. So therefore, due to this UVL, so we are going to have a downward deflection, and due to this reaction RB, you are going to have a upward deflection. Therefore, the net deflection at this point is considered as a 0. So this is a consistency condition we are taking. So you can see this figure. So this is a cantilever beam first part. So for this cantilever beam with an external load that is applied W kilonewton per meter. So here the deflection will be in the downward direction. So the deflection at this B is given by delta B, that is WL power 4 by 30 EI. So these all derivations have been done in the deflection of beams for a cantilever beam. This is a formula for finding out the deflection when we are having a UVL load. So then the deflection is given by WL power 4 by 30 EI. After writing this, again we have another beam, that is a cantilever beam. This is a second part, which is having a upward reaction at this B support. So due to this upward reaction, we are having a upward deflection at this B support due to this RB. And this is given by RB into L cube by 3 EI. So this is an upward deflection. Therefore, the net deflection at this point will be equal to 0. That means as there is no external settlement has been occurred in this support, therefore I am considering the net deflection to be 0. Now we are equating this downward deflection to the upward deflection, that is consistency condition. So this is the condition. Net means by adding these two, you are going to get 0. So as they are in the opposite sign convention, I am equating. So now by solving this, I am getting RB as WL by 10. And by using this RA plus RB is equal to total load, that is WL by 2. I am getting RA as 2WL by 5. So these are the reactions we calculated, RA and RB. In the next one, we are going to calculate the momentum. So after getting the reactions RA and RB, I am going to consider moment at B is equal to 0. So by considering moment at B equal to 0, so I am having RA and this external load as well as this momentum. Therefore, I am writing minus MA, which is in the anti-clockwise direction, and then RA into L, which is in the clockwise direction, and minus this external load into this centroidal distance. So the external load here is total area of this triangle, that is half into W into L. So this is half into W into L. And the CG distance about this B point will be equal to 2L by 3. So that is 2L by 3. So by substituting RA value and simplifying the above equation, we are getting MA as WL square by 15. So we got the positive value. That means that whatever the sign convention we are considering for MA, it is correct. So this sign convention is nothing but a hogging momentum. So the direction we are considering it like this, and we are considering the moment as in the positive value only, but the moment here is hogging momentum. So the direction here, it is important. This is how we are going to find out the momentum. So after calculating the moment, then we are going to draw the shear force diagram. For drawing a shear force diagram for this picture, for this beam, so first I'll write down all the reactions RA, RB and MA. So RA and RB are in vertically upward and MA is in the hogging direction. So then I'm going to take the section from B support. Therefore, I'm considering X is equal to 0 at B support. And similarly, X is equal to L at the A support. So the limits are from 0 to L. Here I am going to take the section XX, so which is at a distance of X from the B support. So the intensity of the load, I have to write it here. Why? Because here X is equal to 0 at B, and whereas X is equal to L, I am having a W kilonewton per meter. So at X is equal to distance, what is the intensity of the load? So W load is there for L distance. Then what is the load that is there for this X distance? So by considering similar triangles, I am getting it is Wx by L. So this ordinate is Wx by L. So when you consider X as 0, So the load here is 0. When I consider X as L, the load here is W. Therefore, the varying load is Wx by L with respect to the X distance. So this is an intensity of the load. Now, I am going to write the shear force at a section XX. Before writing this, we are going to see the sign convention. So towards the section, if on the left hand side or on the right hand side, if the shear force is in the clockwise direction towards the section, then I'm considering the shear to be a positive shear. When towards the section, if I'm getting a anti-clockwise direction, then the shear is considered to be a negative shear. So this is a sign convention we are following. Now I am writing a shear force equation. So here RB is in anti-clockwise direction, therefore minus RB, and this load is in the clockwise direction towards the section. Therefore, the area of this load is half into Wx by L into X. So this is the total load that is acting here. So for the limit 0 to L. So when I substitute X is equal to 0, I'm getting shear force at B as minus WL by 10. And when I substitute X is equal to L, I'm getting the shear force to be 2WL by 5, which is a positive value at A support. So this is a shear force at X is equal to 0, and this is shear force at X is equal to L. So after getting these values, we are going to plot the we are going to find where the shear force is equal to 0. Why? Because here the shear force is changing from negative to positive. So at some point it is equal to 0. So now I am equating this shear force equation to be 0. Therefore, I am getting X is equal to L by root 5, where we are going to get shear force to be 0 from the B support. Now drawing a shear force diagram. So this is AB support. So at B support, we are having WL by 10, which is in the negative value. And at the A support, I am having a positive value of 2WL by 5. That is a positive value. Since it is uniformly varying load, and at some X is equal to L by root 5, I am getting the shear force to be 0. So as it is varying, so it will be in the curve shape. So this is how you are going to have the shear force diagram. So we are having at B negative shear force, at A it is a positive shear force, and from B X is equal to L by root 5, I am getting a shear force to be 0. So this is how you are going to draw the shear force diagram. Coming to the next slide, we are going to draw the bending moment diagram. So same way, I am going to consider this proper cantilever beam. So for this proper cantilever beam, so these are the reactions and the moments. Now I am going to take the limits to be X is equal to 0 to X is equal to L. And here it is a section I am considering. So this is a section X. And the intensity of the load here is Wx by L for this section. Now I am going to write bending moment at XX section. So this XX section. For that we are going to we are going to see the sign convention now. So the sign convention here is when we cut a section at this point, the arrows heading towards the section upward, then it is a sagging moment. For sagging moment, towards left, it is in the clockwise direction. Towards right, it is in the anti-clockwise direction. But the arrow here should be heading upwards towards the section. Similar way, when we cut a section, if the arrow is heading downwards towards the section, then the moment here we are going to consider it to be a hogging moment, and the moment is negative moment. So here also left hand side we are having a clockwise moment, and right hand side we are having, left hand side we are having an anti-clockwise moment, and right hand side we are having a clockwise moment. Now when we write a bending moment at this section, so RB here I am having it in a upward arrow, and arrow is heading towards the section in upward direction. So that means it is positive. So RB into X, and this arrow is heading downwards. That means it is the negative of this area. So negative of this area is minus half into, this is Wx by L as I wrote here, Wx by L into X. So this is the area. And the CG distance here is the 2x by 3 from this B support. So that is 2x by 3. And the limit here is 0 to L limit. Now, when I substitute x is equal to 0, I am getting bending moment as 0 at this B support. And when I am substituting x is equal to L, I am getting the moment to be WL square by 15, which is the negative value. So that is your x is equal to L portion. So this is a bending moment at x is equal to 0 and x is equal to L. So after finding the bending moment, then what we are going to do is same, we have to consider the same sections and all. And this is the same sign convention we'll follow. What we are going to do is we are going to find maximum bending moment. So maximum bending moment is going to occur where you are going to have the shear force to be 0. So the shear force has been 0 at x is equal to L by root 5 in the previous slide, as from the previous slide. So when we substitute at x is equal to L by root 5, I am going to get maximum bending moment to be WL square by 15 root 5, which is a positive value. Now, as we know that maximum bending moment is positive, and at A I am getting a negative moment. So at some portion, I am getting the bending moment to be 0. So as the sign convention has been changed. So now I am equating the bending moment equation to be 0. Therefore, I am getting x value as 0.775 L. So at x is equal to 0.775 L, I am having the bending moment to be 0. So after getting all these values of the bending moment, we are going to plot the bending moment diagram. So this is a AB beam. So for this, at B, I am getting a bending moment to be 0. At A, I am getting a bending moment to be a negative value of WL square by 15. And at x is equal to L by root 5, I am getting a maximum bending moment of WL square by 15 root 5, which is a positive value. And at x is equal to 0.775 L, I am getting a bending moment to be 0. That means it has changed from positive to negative. Now I am going to join this from 0, it is getting a maximum value at L by root 5. Again, it is getting to be negative at this A support, that is at x is equal to L, WL square by 15. So at x is equal to 0.775 L, you are getting a bending moment value to be 0. So this is how you are going to draw the bending moment diagram. These are some of textbooks and references. Thank you.